Hey guys, it's Miss Bradford here. I have some sample calculations for you for Charles's Law, which is the most recent homework assignment I've assigned on Microsoft Teams. I'm going to read the problems to you and kind of point out some things you have to do with the data before you do your calculations. And this video, along with your reading, you should be able to do your homework just fine. All right, so when you're reading the problems, make sure you take note of the initial data or the initial conditions for which the gas is being observed and the final conditions for which the gas is being observed. And for all of these problems, pressure is being held constant, so therefore pressure is not part of the calculation. All right. If we look at the first problem here, it says the temperature inside the refrigerator is 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius and has a volume of 5 liters. So the initial conditions are a temperature of 22 degrees Celsius. See the initial right there. The initial says what we're starting with. So my initial volume is 0.5 liters and my initial temperature is 22 degrees Celsius. You have to change Celsius to degrees Kelvin. And in order to do that, you're going to add 273 to 22, which I've done right here. And that gives you a temperature of 295 Kelvin. You have to do that for all your temperatures that are in Celsius. So the final temperature in the refrigerator is 4 degrees Celsius. And to change that to Kelvin, I make that 273 plus 4, which gives me 277, and there should be a K right here, even though there isn't, letting you know that that's Kelvin. Let's see if I can get that written correctly. All right, there you go. All right, then we're going to plug everything into this final equation here that we're going to use for all our calculations. The initial volume over the initial temperature, set that equal to the final volume over the final temperature. All right, and when I plug all of that into my equation, it's going to look like this: 0.5 over 295. Set that equal to X, because I don't know what the volume is, and 277, which is my final temperature. And now this looks like a proportion that you did in algebra, okay? Which is real simple. You cross multiply and then divide. So if I take this and simplify it, that's going to end up looking like this. Let's see if I can put it over here. 0.5 times 277 is equal to 295x. Divide both sides by 295. So in your calculator, to solve for that volume, you take 0.5 times 277 and divide it by 295. And the volume you should get is, X is going to equal 0.47 liters. Now I did round that. In the calculator, you get 0.46949 and some other numbers. So I did round that to 0.47, okay? So that's your first example. Let's go on to the next one. All right, the next example, we have a sample of gas whose volume at 27 degrees Celsius is 0.127 liters. So those are my initial conditions. My volume is 0.127 liters, and my temperature is 27 degrees Celsius. Well, I need to convert that to Kelvin. So 27, right here I do that, 27 plus 273 equals 300 K. Then I go on to read that, let's see, the gas is heated at constant pressure. So again, I don't have to worry about the pressure until the volume becomes 0.317 liters. So that's the final volume. So what is the final temperature in Kelvin? So we're going to set this up. V1 is 0.127 over T1, which is 300. Set that equal to V2, 0.317 over, I don't know the final temperature, so I'm going to call it X. When I cross multiply, I get 0.127 X equals 300 times 0.317. And then I'm going to divide just like I would in algebra. And therefore, my x is going to equal, when I take 300 times 0.317 and divide it by 0.127, that value becomes 749 Kelvin temperature, right? That's the final temperature after the gas is heated. It expands, all right? Any questions? Be sure to email me. I'll be happy to answer them. But hopefully between this video and watching Tyler DeWitt, you'll be able to do these just fine. All right, the next problem, problem number 3, example number 3. I have a hot day. You may have noticed that potato chip bags seem to inflate, even though they have not been opened. If I have a 250 milliliter bag at a temperature of 19 degrees Celsius, so those are my initial temperature and volume. So I have 250 milliliters, and my temperature is 19 degrees Celsius, and right here I convert that to Kelvin by adding 273. All right, let's read on. I leave the bag of chips in the car, and the temperature in the car is 60 degrees Celsius. Again, I want to change that final temperature of 60 degrees Celsius to Kelvin. So I add 273 to it. And the question is, what is the final volume of the bag of chips? So we're going to plug all the information in. That's going to be 250 over 292. Set that equal to x over 333. So when I cross multiply, I get 250 times 333. Set that equal to 292x. I'm going to divide both sides by 292. And so when I take 250 times 333 and divide it by 292, the new volume, x, is going to equal, this is problem 3, 285. Units are going to be milliliters because my initial volume was in milliliters. Okay, that didn't come out good. Let's do that again. There you go. All right. So whatever your initial units are in, your final units are the same. All right. So it's 285 milliliters. And of course, I rounded that because in your calculator, you're going to get 285.1027. And I know some of you are real sticklers about that's not what was in my calculator, but it is. I just rounded it. Okay. Question number 4, example number 4. Reads, a soda bottle is flexible enough that the volume of the bottle can change even without opening it. If you have an empty soda bottle, the volume is 2 liters, at room temperature, 25 degrees Celsius, what will the new volume be if you put it in the freezer at -4 degrees? So my initial conditions are, I have 2 liters, that's my volume, it's at 25 degrees Celsius. So right here, again, I'm changing 25 degrees Celsius to degrees Kelvin by adding 273. I need to know the final volume, and then I'm putting it in the freezer. So my temperature is -4. So I have to add -4 to 273, and I get a positive 269. Okay, that's just adding a negative number to a positive number. Should have done that in algebra. That shouldn't have been a problem. So now that everything is all set up, I can find out what the new volume is. So I'm going to plug everything in. 2 over 298. Set that equal to x, because I don't know the volume, over 269. All right, I'm going to cross multiply. 2 times 269 equals 298x. Divide both sides by 298 because I'm trying to solve for x, which happens to be the volume. And so when you do that, that x value is going to equal 1.8 liters. Again, my units were liters initially, so they're going to be liters for the final. All right, and in the calculator, I did get 1.805369. So again, that is a rounded answer for those of you who like to see exactly what's in the calculator. All right, I got one final example for you. To make 300 milliliters of oxygen at 20 degrees Celsius change to 250 milliliters, what must the temperature change to if the pressure remains constant? Remember, for all of Charles' law problems, the pressure is constant, so it's not involved in the calculation at all. I took my 20 degrees Celsius and change it over to Kelvin. 20 plus 273 equals 293. And now I'm ready to find out what the final temperature is. So you take 300 divided by 293, set that equal to 250 over X. All right, now I'm going to cross multiply as I've done in all the others. 300X is going to equal 293 times 250. Then I'm going to divide by 300. So the final temperature for this is going to be 244 Kelvin. And yes, that is rounded because in the calculators you get 244.16666. So it's rounded to 244K. I hope that helps. And I hope you're able to do your homework and no problems. If you do have any problems, just email me and we'll try to get them worked out. Thanks so much. I hope you guys are being safe. Take care. Bye-bye.